now we're going to be doing an example to apply what we have learned in terms of how we can come up with a modeling function being a sinusoidal graph, and then use the modeling function to calculate or predict a value right here. In this particular problem right here, we are now looking at temperature. So let's read the wording description. Outside temperature over a day can be modeled as a sinusoidal function. Suppose you know the high temperature of 73 degrees occurs at 5 p.m. and the average temperature for the day is 65 degrees. Find the temperature to the nearest degree at 7 a.m. All right, so this problem immediately asked us to predict a temperature right at that specific time point right there. So it did not specifically ask us to come up with the modeling function, but in our responsibility, we must be able to come up with the modeling function in order to use that function and come up with the prediction. Okay, and you can see that according to the definition, according to the wording right here, outside temperature over a day can be modeled as a sinusoidal function. So behind the scene, the wording of the problem has already gave us instruction that you gotta find out the modeling function before you are able to come up with a prediction. Okay, and so now once again, now we're gonna repeat that process to come up with the modeling function, and then use the modeling function to come up with our prediction right there. So now let's identify the low and the high in my usual guidelines right here, in my recommended guideline. So suppose you know the high temperature of 73 degrees occurs at 5 p.m. and the average temperature for the day is 65 degrees. The high is 73. The entire wording did not give us a low, but now it gives us the average temperature for the day, 65 degrees. And so being a sinusoidal function, then the one essential idea about a sinusoidal function is that once you put in a high, being 73 degrees, without knowing immediately the low, here's how we can tackle it down right here. The average temperature that was given in the problem is considered as the middle value between the low and the high. Okay, so once again I repeat, even though it was not specifically mentioned, but the average temperature being stated in the wording of the problem is being used at the middle value exactly between the low and the high. And so that means what? I can just call that point down here, somewhere down below 73 being my 65 degrees, being the midline right there. Okay, and so exactly that same space right there, down below right here, it has to be my low. And so numerically speaking, from between 73 and 65, that would be a distance of 8. Okay, so in that way, 8 values below 65 here has to arrive at 57. So now I have put down the high and the low, and the middle value right here, I'm going to put down that center line as dotted line. And that's also the time scale for ourselves right here, the time axis for ourselves right here. Okay, so temperature going up and down and down periodically throughout every day. Okay, and so now that's how I started out first, according to my general guideline right there. And so now the next step I'm going to do is I'm going to look for a starting point. Throughout the wording, the starting point is nowhere given in this problem right here. So that means we have our control over choosing a starting point. Okay, and so one more time, let's look back at the wording of description of the problem right there. So we know that the high of 73 degrees occurs at 5 p.m. right here, and then nothing else, no other information was given. But we know further it's the way how temperature is. It's rising and it's dropping and it's rising and it's dropping throughout the day. So throughout the day, at some point it hits high, some other point it hits low. But the idea now is that it's gonna come back to the exact point at exactly 24 hours later, as 1 day later. Okay, so we take advantage of that understanding. Once again, the temperature throughout the day rises and come back rising like that. But it will have to definitely hit the exact same temperature exactly 24 hours later. And so in that way, now again, into what I was saying, we can choose a starting point. So right here, in this given information, as a given data, 73 degrees to be high, that happens at 5 p.m. So this time point right here, let's call that time point our starting point. So right on my chart here, I call that time point, 5 p.m. And so at that time point, my given data gives me a plotted point being up there. Because at 5 p.m. on any day, on a day, we hit a high, 73. Okay? And then so, in what I have explained earlier, and even though it was not particularly stated in the problem right there, it must come back to the same temperature at exactly 5 p.m. of the next day, exactly 24 hours away from that starting point that we have chosen. So this starting point right here, I have chosen it, and that's t equals 0. Okay? And then so exactly 1 day later, I have to have another point that's plotted there exactly the same height, but 24 hours away. All right? And so from that way right there, then we can start tracking down the other plotted point even though they were not given. We can start putting down those other plotted points right there. And so the wording of the problem already instructed us that we are expected to come up with a modeling function as a sinusoidal function. And so in that understanding, in the way of being a sinusoidal function, halfway, now it starts high, midline is here, halfway throughout the complete cycle, then any sinusoidal function has to hit, in this way right here, it has to hit a low right there, right? So in this way, it starts high, and it's going to have to swing low right here. And you're starting to see where I'm going with that. Okay, so it has to hit 57 right here at exactly, so 12 hours away from 5 p.m. right there. That's making it 5 a.m. in the morning. And so, and then 6 hours away, being our first quarter of 6 hours away from the starting point right here. That's 11 p.m. It will drop down to hit the midline. So we should have a plotting point here, a plotted point there. And so like I said, because being a sine function, I mean, if it was a sine function, it's going to have to start somewhere on the center line right here. So we take that middle line as our center line there, and then it's swinging up and down as a sine. But here it starts high away from the center line, and it drops low. And so now it's clear that at the third quarter right here, which is 11 a.m., it's going to hit back to another midpoint value right here, midline value right here. Okay, so now I'm going to fit a sinusoidal graph through these plotted points right here. All right. So these plotted points, a lot of times we have to think logically in terms of that, and we were driven into that direction because of the wording that we have to use either one of the two functions, sine or cosine, because it's a sinusoidal function. And so it has to be a cosine in this case because it starts high and ends high right there. Okay, or basically it starts away from the center line. Okay, and so now we've come up with a graph, and just one basic unit is good enough. And so now I'm seeing this as y equals some coefficient cosine of a times t minus the starting point plus k. And I'm going to come back to the other board and start, identifying the information. So with this portion of our graph right here, yes, our center line is at y equals 65. Okay, y equals 65. That's our center line. And then the high temperature and the low temperature being 8 values away from the mid temperature right here, the middle, the average temperature. So in that case right here, I recognize an amplitude being 8, because once again, the highest it hits is 73, 8 values above from the midline. and then the lowest temperature, 57, 8 values below, and that's how I recognize the amplitude. And so now I have enough information to come back to the other board and partially fill in my function. So now we can partially complete our function as y equals 8 for the coefficient times cosine of, we haven't found a, let's leave it there, t minus c, plus, but now that center line here is 65. Okay, and so now I don't need to have a negative in my coefficient in front of the cosine function, simply because the shape of our cosine was already in its ordinary form. So now back to the graph, let's identify further information. So now I can see that period was given to be, and it's known, it was not even mentioned, but we know it has to be 24 hours, so period equals 24. And further, we know that we chose the starting point, to be t equals 0. Okay, and so now with that information, it's further enough for me to swing back on the other board. And so now, again, sine or cosine, generally we'll have period being 2 pi over a. We want to equate that with our known period for this particular function we're looking for, being 24. And so solving this equation, we're going to lead down to a equals, must be pi over 12. Pi over 12. And now upon having a value calculated, I can further complete our function here. Y equals 8 cosine of pi over 12 times t minus c plus 65. All right. And now further, with our starting point being given, being identified as t equals 0, list it down on the other board right there. Then we must substitute this into our starting point, our general starting point in the function form. And so that means we're looking at y equals 8 times cosine of, now I have a pi over 12 times t minus 0 plus 65. And now my final function here. So temperature, how about a capital T function? As a function of time equals 8 cosine of pi over 12 t plus 65. So now we have completed our modeling function. Now we want to use the function to predict the temperature to the nearest degree at 7 a.m. All right. So keep in mind that 5 p.m. I chose to be the starting point. It's to be t equals 0, our starting point. Okay, and so 7 a.m. is going to be understood as 14 hours away from that starting point. Okay, because 5 p.m. of some day is here. Another 24 hours, another 5 p.m. of the next day. Halfway, 12 hours away, we're looking at 5 a.m. Exactly halfway through the day, 12 hours away from that starting point. And so 7 a.m. has to be another additional 2 hours away from that. That's how I come up with t equals 14. And so now to predict the temperature at 7 a.m., it is exactly the function value for temperature at t equals 14. I substitute 14 into the function. So substituting that into the function, we're looking at 8 times cosine of pi over 12 times 14 plus 65. And we can reduce this a little bit before doing some actual work with that. So that's making it 8 cosine of 7 pi over 6 plus 65. And so now on the calculator, 8 times cosine of 7 pi over 6 plus 65. Or in decimals, 58.07179677 and a lot longer. But so now, according to the rounding requirements of the problem right there, round to the nearest degree, then we're now looking at just about 58 degrees. That what it says is to the nearest whole degree right there. So it's about 58 degrees, okay, at 7 a.m.